Herbal medicines rely on complex biological inputs. When raw plant material carries undeclared toxic species, heavy metals, or microbial contaminants, the finished pharmaceutical product becomes a vehicle for those hazards. Over the last 2 decades, global utilization of herbal medicines has expanded rapidly. Correspondingly, health authorities have recorded a sharp spike in adverse patient events, directly linked to raw material toxicity and poor quality control at the source. The pharmaceutical industry often treats quality control as a downstream manufacturing step. You cannot take heavily contaminated, misidentified plant material and retroactively engineer safety into the finished extract. To secure the botanical supply chain, the World Health Organization intervened with a standardized operational mandate. They established the Good Agricultural and Collection Practices Framework, or GACP. It provides precise technical guidance on the cultivation, collection, and processing of medicinal plants. GACP operates as a strict risk mitigation architecture. It forces producers to standardize highly variable biological inputs in the field, long before those materials ever enter the manufacturing stream. Securing a botanical supply chain begins at an absolute 0 point: botanical authentication. Regulatory standards require that any cultivated or wild-foraged species strictly match the specific botanical variety listed in the end-user country's national pharmacopoeia. Whether accidental or intentional, species adulteration introduces foreign compounds into the supply chain. Every single medicinal plant must have its scientific name, genus, species, and subspecies, mapped and verified against official monographs. In cases where a plant is newly introduced or botanical ambiguity exists, producers must submit a physical voucher botanical specimen to a regional or national herbarium for formal identification and archival. The propagation materials themselves are equally scrutinized. Seeds must be demonstrably unadulterated and free of disease to prevent the introduction of baseline pathogens into the soil. Ultimately, a failure in this initial authentication phase invalidates every subsequent quality control measure. A perfectly processed toxic weed remains toxic. Once identified, raw materials are sourced through 2 distinct operational pathways: good agricultural practices for cultivated plants and good collection practices for wild foraging. This grid displays the engineered environment of good agricultural practices. Soil pH, moisture retention, drainage, and targeted irrigation are strictly controlled variables that directly dictate the plant's intrinsic chemical synthesis. To prevent dangerous infectious microbial loads, the framework strictly prohibits the use of untreated human excreta as fertilizer, requiring any animal manure to be thoroughly composted to destroy pathogens. Growers must also implement integrated pest management. This limits necessary agrochemical applications to the absolute minimum, ensuring residual pesticides remain well below international regulatory limits. This map highlights the shift toward defensive ecological mapping under good collection practices. Field workers must navigate unmanaged habitats to extract specific plant populations without compromising their survival. Collection protocols mandate ecologically non-destructive harvesting. When targeting root systems, collectors are instructed to sever only the lateral roots, leaving the main taproot intact to ensure the long-term survival of the local population. When harvesting bark, workers take longitudinal strips along one side of the tree. Completely girdling the trunk cuts off nutrient transport and kills the source. The framework also establishes strict geographic exclusion zones. Foraging is prohibited downstream from active livestock pastures or near industrial runoff to prevent extrinsic microbial and chemical contamination. Executing this requires local field workers to have formal botanical training. They must distinguish the target species from morphologically similar toxic flora to ensure both product purity and personnel safety. While agriculture relies on absolute environmental control, wild collection relies on sustainable demographic controls. Both architectures are required to secure a pure baseline material. The transition from the field to the processing facility is governed by the harvest window. Here, producers face an inherent conflict between physical mass and chemical potency. This chart plots total vegetative mass against the concentration of biologically active constituents. The data reveals a critical divergence. The maximum concentration of active chemicals occurs independently of the plant's maximum physical growth. The rules mandate that the precise timing of the harvest must be dictated solely by peak constituent concentration, even if it means sacrificing overall vegetative mass. The physical harvest operates under stringent environmental constraints. Cutting in wet conditions, during rain or high humidity, is avoided to proactively prevent baseline microbial fermentation. The absolute baseline rule of field collection is physical isolation. Severed raw material must never come into direct contact with bare soil. Once cut, the highly vulnerable material requires prompt transport in clean, aerated containers to indoor drying facilities before thermal degradation and enzymatic breakdown begin. Executing the harvest at this precise window preserves the peak concentration of active compounds. This timing prevents the immediate degradation of biological material that occurs after the plant is severed. Drying, sorting, and primary processing represent the supply chain's most critical vulnerability window for cross-contamination. Drying parameters must be custom calibrated for specific botanicals. Utilizing shade drying or controlled lower temperatures prevents the destruction of volatile natural substances like essential oils. This schematic outlines the post-harvest facility. Its architecture is an engineered defense mechanism against biological and chemical contamination, divided into dirty areas and clean areas. Hard physical partitions isolate the dirty zones, used for unloading, soil removal, and milling, from the clean zones, used for drying and final bulk packaging. This enables a strict unidirectional flow of materials. Raw inputs move sequentially from dirty zones to clean zones, without their paths ever crossing, eliminating cross-contamination. Facility ventilation is equally engineered. Airflow must strictly move from clean zones into dirty zones, actively preventing dust and microscopic spores from blowing backward onto processed materials. The physical surfaces of the facility must be waterproof, non-absorbent, and sealed without crevices. This eliminates microenvironments where pests and pathogens harbor. Living quarters, animal areas, and effluent waste disposal systems must be completely separated from the processing footprint. The facility requires distinct potable water systems for washing and wet sterilization, utilizing entirely separate piping from any non-potable lines used for fire control or refrigeration. A processing facility is an engineered tool. It finalizes the transformation of a vulnerable harvested plant into a stabilized, standardized medicinal material. Botanical authentication, cultivation and collection protocols, precision harvest timing, engineered facility architecture. These four sequential phases establish the good agricultural and collection practices framework. Only once this foundation is established can good manufacturing practices be reliably applied to the final extraction and packaging stages. By systematically controlling intrinsic biological variables and extrinsic environmental factors, the GACP framework neutralizes supply chain risk before processing begins. Strict GACP compliance serves as the mandatory first step for modern, globally compliant herbal medicine production. Without a rigorous engineered foundation in the field and processing facility, no manufacturing practice can guarantee the safety and efficacy of the final herbal product.